without further ado, I'd like to introduce our first speaker, who is Iain Young, and is going to talk about replacing PSK with... replacing AFSK with PSK. Iain.
Thank you very much. Hopefully everybody can hear me. As Trevor just said, I'm Iain Young, call sign G7III, email address is G7III@G7III.net. Awful lot of imagination needed there. So, anyway, replacing 1200 baud AFSK FM with PSK and deploying DTN. To be honest, I tried to come up with a snazzy title but failed. So you got stuck with this one. So, okay, fine. Okay, first of all, what are we going to talk about this morning? We'll do a couple of introductions. We'll talk about exactly what we're planning to replace, because it might not be what you think I'm planning to replace. We'll talk about why we should replace it. We're going to have to do a bit of computer network theory, I'm afraid. It's only one slide. We'll talk about how we replaced what we replaced, the tools and utilities we needed. We'll talk a bit about the RF setup and a couple of maps. We'll actually see the AX.25 get established over PSK rather than FM. We'll then add TCP and UDP to it, and we'll also then add delay tolerant networking over the top of that. Finally, we'll get round to looking at some results and hopefully draw some conclusions, and we'll then talk about the future and a few thank yous and acknowledgements. So that's the plan. So first of all, just a couple of introductions. We are going to focus on two major areas for this presentation. One is replacing AX.25 1200 baud AFSK FM with PSK, and the second is deploying DTN, which we've probably already covered, but now who's doing this? Well, myself, who happens to be the MaxPack chairman, and Dave Maydew, who can't be here today because he has a wedding engagement, not unlike some others I know. Seems to be a theme this year, who is a member of our committee. Now, MaxPack was formed many years ago as a dedicated AX.25 packet group for the Midlands, but a couple of years ago we modified the constitution to include all digital modes, because way back when it was formed, AX.25 was a digital amateur radio, whereas today there's a lot more modes out there. So what are we going to actually replace, and what are we not replacing? We're replacing the AX.25 physical layer. In network parlance, we would call it layer 1. What we actually mean is the 1200 baud AFSK FM transmissions. We're not replacing what network world would call layer 2, or the data link layer, where you send and receive actual AX.25 frames. Okay, the mode we're all familiar with, right, would more formally be described as AX.25 over the 1200 baud AFSK FM. Bit of a mouthful, and the mode we'll be creating more formally could be described as AX.25 over PSK. So, why are we doing this? I mean, like any experiment, we need a why. Well, let's face it, 1200 baud FM is not exactly well known for its efficiency in spectrum usage, power requirements, and link budget. And to be honest, even its 300 baud cousin's not particularly well thought of on HF, especially these days. It's not the thinnest slice of spectrum usage there is. And frankly, that's only a quarter of the throughput. Plenty have claimed that PSK is superior. But has anybody actually got any figures? Because it's pretty difficult to find real world figures. So can we actually...
Just a remark. We have a lot of atmospheric simulation review, and with PSK, your satellites can get a few frames per. However, with FAC and FUNK,
Oh, yeah. I'll come on to a bit of FEC towards the end. Yeah. Yes. Yeah. But yeah. So, what else do we want to do it? Well, you can eliminate the dedicated hardware TNC. Most of us have already got a sound card interface, and one of the issues with Packet is that need for a dedicated TNC. People don't want a dedicated box that they can only use for one thing these days. When they've got a sound card interface, it'll do any mode they want. We can do better. We need to do better, to be honest, especially after all these years. And the last line, well, just have some fun. Right, this is the network theory part. Now, I know this is a more radio-orientated audience, so I'm going to gloss over a lot of this, but I think it's important that we get some of the basic concepts across. Some of you that might work in a similar field to me will already know this and will probably berate me later for simplifying it so much, but it's more important to get the basics across. In computer networks, we have this thing called the ISO model, or the OSI model. Don't ask me which one is which, I never remember. And it divides the network up into different, what it calls layers. Now, I'm going to start off at the physical layer because that's the easiest to understand. There are 7 of them. We're only going up to about layer 4. We'll skip 5 and 6. Layer 7 is an application. So, what I'm going to talk about first is the pure ISO OSI model. The truth is, nobody implements the model correctly in its entirety. Everybody does something a little bit outside the spec. But let's start at the physical layer. The physical layer defines how data gets transferred across a wire or across a radio link. It defines things like voltages, currents, frequencies, tones, that type of thing, type of cable to be used. That's all. There's no intelligence there. It's just effectively how do you put a 1 and 0 on the wire. Nothing else. Okay? Let's get that one pretty simple. The layer 2, the data link layer, that is responsible for one station to be able to talk to another station on the same link. And it is only point to point. It can allow multiple stations on the link, but it only says you can get data from A to B. That's all it does. That's what it's responsible for. A typical data link layer you would know about would be Ethernet. Okay? And in our case, AX.25, but we'll come on to that in a minute. As we move up to layer 3, well, we had these 2 stations that were talking A and B perfectly happily. But what if they are the other side of the world from each other? They're on different links. So the network layer is responsible for getting data from A to B when it has to go through C, D, E, F, or wherever. Okay? Now the transport layer up at the top there. The transport layer I'm going to very much gloss over. However, the easiest way from our perspective to look at it is it allows us to run multiple applications on the same machine, on the same node. You will hear definitions like TCP port number and UDP port number. So for the context of this discussion, see it as a multiplexer. That's the easiest way to think of it. So that's the diagram on the top left there. Now, okay, if we look at the top right, a typical home network. For the physical layer, things like Wi-Fi, Cat5, Cat6, that type of thing. Your data link layer is almost certainly Ethernet. Your network layer is the Internet Protocol or IP. and then your transport layers would be TCP and UDP on top of that. Most of you are probably used to that to some degree. Now, let's look at a typical AX.25 setup. Instead of Wi-Fi or Cat5 or Cat6, we've got 1200 baud AFSK, or we've got 300 baud FSK on HF. For a data link layer, we've got AX.25. I say L2 here. I have expressly separated that because AX.25 defines both the physical layer and the link layer. What did I say about nobody adheres to the model? Up at the layer 3, typically in use you would have things like NetROM and rows, but you can also run IP over it, and then you can run TCP/IP over the top of it. Now, the diagram in the bottom left, sorry, the bottom right, you will notice it's quite similar to the one in the bottom left, but it adds on top of the AX.25 layer and on top of TCP and UDP something called the DTN bundle layer and a number of layers that end in CL. These are the DTN, the delay tolerant network layers that we will get to later. But in brief, the ones that are in yellow are what we call convergence layers and run over the top of their parent protocol, if you want to look at it that way. What they allow is the DTN bundle layer to communicate to other DTN bundle stations using any of the convergence layers available. What I really want to get across here is how you can layer the protocols on top of each other. Okay, so you can layer, TCP and UDP is layered on top of IP, but you can put the DTN, TCP, and UDP convergence layers on top of that, and so forth. Right, okay. That's the end of the network theory, for now anyway. How did we do it? Well, there is a beta version of FLDigi out there that can act as a software KISS TNC instead of a hardware TNC. But since it's software, we need a sound card interface to get to the rig. We need the Linux AX.25 utilities. They're all pretty much available in most distributions. But we also needed a utility to link FLDigi to the rest of the AX.25 stack. Just a quick note, Linux is unique in operating systems in that it's got full AX.25 support in the kernel, just like others have Ethernet and TCP/IP and things like that. So it just treats AX.25 as any other network protocol, which does have benefits. So the extra utility we needed was something called SOCAT, or socket cat. It forms a pipe between two different types of sockets. Now that could be a file, it could be a serial port, it could be a pseudo terminal, it could be a TCP port, a UDP port, anything essentially. It's a very useful utility. And since KISS TNCs are essentially pseudo terminals, which are essentially the same as a serial port, one end can connect to a pseudo terminal, while the other is connected to the appropriate UDP port for FLDigi. What this allows us to do is it allows us to run FLDigi on the local machine or on a remote machine halfway across the network, which does also have benefits. So, since many of you probably won't have hooked up Linux and AX.25 via a traditional TNC, this is the way you would normally do it. Just a couple of notes first, though, about this diagram. The colors are consistent, with the diagram I showed earlier. So a red backgrounded box is going to be a layer 1, a physical layer thing. Boxes, in this case, are physical devices, while the ellipses are actually processes, i.e. programs running on the machine. So what we have here is we have a TNC. It's connected to a physical serial port. Often they have TTYS something or USB something. We then have a process called KISS attach. This actually attaches the TNC as a KISS device to the kernel. I've shown the kernel AX.25 port there just for clarity. We then have the rest of the network stack, and then we have all your AX.25 applications, linFBB if you want to run FBB, the node, all that type of thing. That's the traditional way you would do it, with a physical hardware TNC. With a software TNC, using FLDigi, you can see that the top half of this diagram is very, very similar. From KISS attach onwards, it's identical. However, before we get to KISS attach, if we look, we've got the signal link SL1 in my case. So the sound card interface, it's talking to FLDigi at a physical level, i.e. it's just tones and phase and that type of thing. That talks to a UDP KISS port instead of instead of a physical serial port, and we have SOCAT there, which is acting as an interface between the KISS the KISS port and the pseudo terminal that KISS attach is expecting. So that's how you would actually hook it up with a software TNC. So what was the full setup we used? Well, at my location, we had an 847, one of my 680 cross quads. I used the Raspberry Pi to run the AX.25 stack, and I have a rather nice big multi-core machine that does SDR work. So that was running the FLDigi. Over at M0DCMs, we had the 857, a collinear instead of the quad, and only one machine. And initially, tests were done at 50 watts, but then we suddenly realized that 5 watts would suffice quite by accident. We wanted to make sure we had a good link. And we did carry out further tests at 20 watts on 70. Right, I'm going to have to go quickly through this because I know I'm running out of time. This is the basic network diagram. On the right-hand side, we see the setup at M0DCM's location. I've shown the stack. I've shown SOCAT. I've shown FLDigi up through the sound card interface over the RF link, and you can see the same, similar on my side, except that I'm running FLDigi on a separate machine. The thick boxes are physical machines. Oscar, which was cunningly named because I was thinking about doing this presentation when I was doing it, is a separate machine that only has TCP and doesn't have any radio connections. But hopefully we'll get to that. So, what does this allow us to do? Well, we can connect to each other over AX.25. We can use all the AX.25 facilities. But rather than 1200 baud FM, we connect using PSK. PSK 125, 250, 500, or whatever we like. But being Linux, we can go further than that. We can add TCP and UDP very easily. We just need to add an IP address to the kernel interface, and we've done it. And so we were able to do that, and we were able to ping each node, and we were able to transfer UDP packets and TCP packets. We did get a problem with TCP and handshaking. Never entirely got to the bottom of it, but we think it's the length of time Dave's interface was taking to switch between transmit and receive. That gives us the full ability to run full IP stack, so we can do DNS, HTTP, NTP, which we did do, SMTP, POP3, any standard protocol. But being Linux, we can go one step further and add DTN. What is DTN? Well, we've had talks about DTN here in the past, so I'm not going to go too much into it. But it's really designed for noisy, unreliable, or non-constant links. It consists of a bundle protocol, which sits on top of a number of convergence layers, which are used to transmit the actual messages and files you want to transmit. It allows nodes with different convergence layers to communicate, as long as an intermediate node or nodes have the needed convergence layers, i.e. there's a set that allows you to communicate together. Typically, a convergence layer will be layer 2, such as Ethernet or Serial, or layer 3, TCP or UDP. The reference implementation that is out there, it's also known as DTN2. Got some interesting convergence layers for us. UDP and TCP, yeah. But it's also got AX.25 connected mode. And since we've already got AX.25 and TCP IP configured, over PSK, we can set up a DTN network using, well, the whole stack. So we did. Now the DTN network layers, this is a similar diagram to the one you saw before. The one on the left is Oscar, which is a small machine. It's only got TCP, as you can see there. My node in the middle has TCP, UDP, and AX.25 DTN support. And Dave's node on the end has UDP and AX.25, no TCP. So we can transfer messages from Oscar to M0DCM because G7III in the middle there supports both sets. And yes, I could have used Ethernet over between Oscar and myself, but TCP is easier. So what were the objectives? Well, prove that we can replace AX.25 1200 AFSK with PSK. Prove that we can run DTN over AX.25 over TCP AX.25 and UDP AX.25. Measure the throughput. Measure the improved throughput when using multi-carrier PSK modes. Measure the effect of changing the MTU and or the packet size. How did we do it? Well, first of all, we checked FM and SSB voice worked. We both heard each other, but even at 50 watts, it wasn't great. We checked layer 1 and layer 2 connectivity, checked the waterfall on FLDigi, and we confirmed that we could receive each other's AX.25 beacons. As we discussed earlier, we checked ping, and we used something called Network Commander to do a UDP test. And then we did some transfer tests using DTN and measured the throughput of many PSK modes. A note on the measurement method. We were looking at the raw RF transmission time, not the DTN reported time. There was a good reason for this. You can have some delays in the AX.25 stack. It's up to roughly 20 seconds, and you can't really tell from one transmission to the next as to how long that's going to be. So what were we able to achieve? We can set up the AX.25 network. We could add TCP IP over that. We could run UDP over it. I did it for kicks, but it worked. And yeah, there is an entirely different presentation about that. We were able to add DTN over UDP. We were able to transfer files and messages between the two nodes. We were able to use different PSK modes. The fastest we did was PSK 800 dual carrier. We were able to add that third node I was talking about and integrate that into the network. And we were able to run transfer tests between the two nodes. So let's get some actual results before Trevor winds me up. These are raw figures, and we did have some failures, especially at larger packet sizes, as you can see, due to UDP fragmentation reassembly timeouts. But we think we can fix them. But we can see some of the raw figures there. Now these are all fairly small files, 240 bytes in one case. But do pay attention to the dual carrier PSK 800 mode. It did a transfer rate of 120 bytes per second for a file that was 240 bytes. But if you look carefully, you will see that pretty much every time you double the size, you get more than double throughput. Now, those were very small files that we transferred. The bandwidth column is obviously how wide the mode is, by the way. But I want to go on to the next slide, if I can, because these are, we concentrated on the dual carrier modes. And we can obviously see that PSK 500, 2K file, got 93 bytes a second. Go to dual carrier 800, you get 146. But by fiddling with the MTU size, or the packet size more accurately in AX.25, we were able to significantly improve the throughput and be able to transfer bigger files. A 5 kilobit file, we got up to 186 bytes per second. Now, that's raw figures, not really the objective here. We want to compare against 1200 baud FM. What is the 1200 baud FM bandwidth? Well, it actually varies on your deviation, of course, but it's supposedly 2.5 kilohertz for 12.5 kc spacing, 5 for 25. Saw one software implementation that claimed 3.4 kilohertz. Same source claimed 900 hertz for HF AX.25. So, but these figures are typically measured as plus or minus, not as absolute. So, anybody know a typical deviation figure for an amateur spacecraft that transmits 1200 baud?
5 kilohertz.
Okay, we'll take that. We'll take that. Let's put some context on here. G7III and G7III did some early work on DTN over AX.25 FM, and we can see in the first two rows here their results. Now, they had a file size of 9177 for various reasons. They happen to have it hanging around, I believe. And so over DTN, they were getting 84.7 bytes per second. But that's a bandwidth of 5 kilohertz. If we look at PSK 500 dual carrier, which is the third row with data on it, which is only 1 kilohertz wide note, we were getting 93 bytes per second. If we look at one where we increased the MTU size to 1500, and if there's any network engineers out there, you know where I picked that from, we got 186.2 bytes per second. Now, yes, 800 carrier, dual carrier is somewhat bigger than PSK 500 dual carrier. It's actually 1,920 bytes. Hertz, sorry. So call it 1K9, call it 2K. It's still well less than the FM. I did then get connected mode to work. Doing it. The first set of figures are over UDP. The second set are over AX.25 connected mode. And yes, their experiments beat mine, but I'm pretty sure that is due to my setup not being optimized in any way, and the UDP and AX.25 packet sizes colliding. So just a few conclusions that I will roll up quickly. AX.25 over PSK can be done. We can get better throughput for less bandwidth than its FM cousin. It will work over a noisier channel than FM. I didn't really go into this, but we found out that certainly when we did the voice check, I wasn't expecting very much, and to be honest, we wouldn't have got much on AX.25 FM. You can work over much less bandwidth, but at the trade-off of throughput and efficiency. So HFOps is still possible, but you must get packet lengths and MTUs and timeouts correctly aligned, otherwise it doesn't work that well. DTN, you can deploy it over amateur radio today, but it's very much the lower level protocols. Further work would be needed to integrate it. That said, some of the work, to integrate with SMTP would be fairly simple, and I know people have done it via postfix. I know there is a postfix implementation out there. What didn't work so well? The TCP mode. I think we've discussed why. We couldn't get PSK 1000 to work, even with higher power. But not quite sure why, but we've got one or two ideas, so we'll see. Just some notes on some future experiments. We'd like to fix the packet length issues, different convergence layers, different nodes and higher speeds. USRP and SDR experiments for even higher speeds. Spacecraft links maybe phase 4A, we'll see. An ad hoc network rather than fixed. But one thing I do want to get in is if anybody's within RF range of myself in Coventry or Dave in Walsall on 2 and 70, they got a Linux box, a sound card interface, please get in touch. I can give you installation instructions for most of the bits. If we just add one more station, then we can have people within RF range of them on the network, and so on, and so on, and so on. I think, that's more USRP possibilities, because the USRP can provide far higher symbol rates than FLDigi. So that, you can go as high as you like with that. Consider maybe integrating FreeDV or Codec 2. A Digimode's DTN SDR ground station, anybody? And just imagine what symbol rate you could get, 250 kilohertz. One final bit. A plea to satellite designers and builders, please consider replacing AX.25 FM with PSK, even if you use AX.25 frames. As we've seen, it's far more spectrally efficient. You can add FEC on top of PSK easily enough. The Linux stack wouldn't care. It's beneficial on link budget, requires less signal to noise, although we've not actually quantified that. And as I said earlier, you can trade throughput and for link and or power budget. And today, software is plentiful for decoding PSK. There's plenty of them out there. Anyway, I shall leave it at that because I know Trevor wants to keep things moving.
Thank you.
I do have...
Take any questions just now, but I'm sure Iain will be more than happy to answer any questions you have during the break.
There are a number of sets of bits of paper over on the table over there, which are 3 emails that I sent to the MaxPack group explaining in more detail the experiments that we did. The presentation is effectively a summary of them.
Right, thank you. Right.